Let G be a group, and let S be a subset of the group G. We will denote by S inverse the set of all inverses of elements from S. Now think of the elements in S and S inverse as building blocks. We can create new elements by multiplying any number of building blocks together. Repetition of the same building block allowed. The product of zero elements, the empty product, is also allowed and is defined to be the identity element. The set of all elements we can create this way is called a subgroup generated by S. We denote it by putting angled brackets around S. If H is the subgroup generated by S, we also say that S is a set of generators for H. Let H be the subgroup generated by the set S. As the name suggests, H is indeed a subgroup of G. To prove this, we just need to show that H is not empty, that it is closed under taking products, and that it is closed under taking inverses. As an example, let's consider the symmetric group on n elements. If we take as generating set all permutations, then of course we generate the whole symmetric group. However, we can also generate the symmetric group using a smaller generating set. Indeed, just taking all cyclic permutations suffices, because as we have seen, any permutation can be written as the product of cyclic permutations. In fact, we don't need all cyclic permutations. We've seen that any permutation can be written as a product of transpositions. So the set of all transpositions is also a generating set for Sn. In fact, we can already use a small subset of all transpositions to get a generating set for the whole symmetric group. In exercise 5.1, you will see that the symmetric group can in fact be generated using only two elements, one transposition and one n cycle. Now let's consider the subgroup of even permutations, the alternating group. We have seen that any even permutation can be written as a product of cycles of length 3. So the cycles of length 3 form a generating set for the alternating group. Using exercise 4.14, you can see that in fact a smaller set of 3 cycles already generates the subgroup of even permutations. A subgroup generated by a single element is called a cyclic group. In that case, the subgroup consists of all powers of a single element x. The group of integers under addition is an example of a cyclic group because it's generated by the element 1. Keep in mind that here the group operation is addition, so we're generating elements by adding copies of 1 and minus 1. Similarly, the group Z mod nz is also a cyclic group. For n bigger than 2, the symmetric group on n elements is not a cyclic group. However, it contains cyclic subgroups. The permutation shown here generates a cyclic subgroup of S5 consisting of 6 elements in total. In the multiplicative group of real numbers, the element 2 creates a cyclic subgroup consisting of all powers of 2. Be aware that it should always be clear what group we're working in. If we take the element 2 in the additive group of integers, it creates a completely different cyclic subgroup. As a last example, consider the subgroup generated by the element 2 in the group Z mod 7Z star. Because in this group the operation is multiplication, we get all powers of 2, of which there are 3, 1, 2 and 4 mod 7. Here are some quick questions. See if you can find the answers before moving to the next slide. Remember that operation in Z plus is addition, so the subgroup generated by the elements 6 and 10 consists of all elements that we can make by taking the elements 6, minus 6, 10 and minus 10 and adding them. An element is an integer multiple of 6 plus an integer multiple of 10 if and only if it's an integer multiple of their GCD. So the subgroup generated by the elements 6 and 10 is the group 2Z, all the even integers. The group operation in R2 is addition of vectors. We first show that the two basis vectors are integer multiples of the two given vectors. Any integer vector is an integer combination of the two basis vectors and therefore also an integer combination of the two given vectors. So the integer vectors are contained in the set generated by the two vectors. Of course, conversely, they can only generate integer vectors. So indeed, the two given vectors generate exactly the subgroup of integer vectors in R2. Let x be an element of the group G. Now consider all positive powers of x, x squared, x to the power 3, and so on. If x to the power n is the first power of x that's equal to the identity element, then n is called the order of x. If this never happens, if all positive powers of x are unequal to the identity element, then we say that the order of x is infinite. Consider, for example, the element minus 1 in the additive group of real numbers. This element has infinite order. Indeed, if you add minus 1 to itself any number of times, you will never get the element 0. The element minus 1 in the multiplicative group of real numbers, however, has order 2, because minus 1 times minus 1 is equal to 1, the identity element in R star. The multiplicative group of real numbers only has two elements of finite order, 1 and minus 1. The multiplicative group of complex numbers, however, has many more finite order elements. For example, the element I has order 4. The element 2 in Z mod 11Z has order 6. The element 2 in Z mod 11Z star has order 10. The order of an element in the symmetric group can be easily determined if we first compute a decomposition of the element into disjoint cycles. Then the order of the element will be the least common multiple of the lengths of the cycles in the decomposition. Let x be an element of the group G and suppose that x has finite order. Now consider any integer m, possibly negative. Then x to the power m is the identity element if and only if the order of x divides m. To prove this, we divide m by the order of x and let r be the remainder. So then we have x to the power m is equal to x to the power r. We now consider two cases. If the order of x divides m, that is r is equal to 0, then x to the power m is equal to x to the power 0, which is indeed the identity element. If the order of x does not divide m, that is r is not equal to 0, then x to the power r cannot be the identity element. Indeed, r is a positive integer that is strictly smaller than the order of x, so x to the power r cannot be equal to the identity element. So in that case, also x to the power m is not equal to the identity element. Let H be a cyclic group generated by an element x. The next theorem states that H is either isomorphic to Z or to Z mod nz, depending on whether the order of x is infinite or equal to n. In particular, all finite cyclic groups with n elements are isomorphic. Instead of Z mod nz, we often use the notation Cn, which is the cyclic group of order n generated by a single element alpha of order n. Let's take a look at the proof of the theorem. Let's first consider the case where the order of x is infinite. Consider the map f from the integers to h that sends the integer n to x to the power n. This is a surjective homomorphism. Let's take a look at the kernel of f. The kernel of f cannot contain any positive integer n. Indeed, x to the power n is not equal to e for any positive integer n, because the order of x is infinite. The kernel of f can also not contain a negative integer, because if x to the power minus n is the identity, then also x to the power plus n is the identity. So we conclude that the kernel of f consists of the element 0 only. It follows that f is bijective, and so f is an isomorphism between z and h. Now let's look at the case where the order of x is equal to n. We create a map f from z mod nz to h that sends the residue class of a to x to the power a. This map is well defined because if we take two representatives a and b of the same residue class, then x to the power a is equal to x to the power b. The map f is easily seen to be a surjective homomorphism. To show that the map f is injective, suppose that f of a bar is equal to f of b bar. So this means that x to the power a is x to the power b. This implies that x to the power b minus a is the identity element. By the previous theorem, this means that the order of x, n, should be a divisor of b minus a. But this implies that the two residue classes a and b are the same. So we conclude that f is injective. Since f was also surjective, this means that f is an isomorphism between z mod nz and h. Let's take a look at elements of z mod nz and compute their orders. Consider an element a bar in z mod nz. Remember that the operation in z mod nz is addition, so to find the order of element a bar, we need to find the smallest positive integer m, such that m times a bar is 0 bar. In other words, m a bar is 0 bar, or n divides ma. Since ma is always divisible by a, this is the same as saying that the least common multiple of n and a is a divisor of ma. We now multiply on both sides by the GCD of n and a. We use the fact that the GCD of n and a times the least common multiple of n and a is equal to n times a. Dividing by a on both sides and then dividing by the GCD of n and a on both sides, we see that m must be a multiple of n divided by the GCD of n and a. So we conclude that the order of the element a bar is equal to n divided by the GCD of n and a. In particular, the order of a bar is a divisor of n. For any divisor d of n, we are now interested in the number of elements of z mod nz for which the order is equal to d. A small calculation shows that this number is exactly equal to phi of d. Here's a small example for n is equal to 10. In the top row you see all the elements a bar of z mod 10z. The second row shows the GCD of 10 and a. And in the bottom row we see the order of each of the elements a bar. So for example, the number of elements of order 5 is equal to phi of 5, which is 4. So in the group z mod nz, the order of any element is a divisor d of n. And for every d, the number of elements of order d is phi of d. Of course, the total number of elements in z mod nz is equal to n. So if we sum over all the divisors d of n and take phi of d, this must sum to n. This is exactly Gauss's formula. Coming back to our example of Z mod 10Z, we see that the number of elements of order 1 is equal to phi 1, the number of elements of order 2 is phi of 2, the number of elements of order 5 is phi of 5, and the number of elements of order 10 is phi of 10. So indeed we get 10 is equal to 1 plus 1 plus 4 plus 4. Here are some quick questions. See if you can find the answers before moving to the next slide. The element A is equal to e to the power 2 pi I over 6 has order 6. In the picture you can see A along with its powers. You can do the same thing for any order n. So the complex numbers of modulus 1 contain a subgroup of order n for every integer n. By Gauss's formula, 77 is equal to phi of 1 plus phi of 7 plus phi of 11 plus phi of 77. So to compute phi of 77, it suffices to compute phi of 1, 7 and 11. These in turn can again be computed in the same way using Gauss's formula. Given a group G, we define the order of G simply as the number of elements of G. It turns out that if we have a finite group G and an element X in the group G, then the order of X is always a divisor of the order of the group G. We will prove that theorem later. Now we'll look at the special case where G is an abelian group. So let G be an abelian group with a finite number of elements, say n elements. So we can number the elements of G a1, a2 up to an. Since left multiplication by an element x is a bijection, the elements of G can also be written as xa1, xa2 up to xan. These are exactly the same elements, just in a different order. If we multiply all the elements of G, it doesn't matter in which order we do that, because G is abelian. So a1, a2 and so on times an is the same as xa1 times xa2 and so on times xan. Again, using the fact that G is abelian, we can lump together all the factors x and get x to the power n times a1 times a2 and so on times an. Dividing on both sides by the same factor a1 times a2 and so on times an, we obtain that e is equal to x to the power n. We conclude that the order of x must be a divisor of n. A beautiful consequence of the previous theorem is Euler's theorem. Let n be a positive integer and let a be an integer, such that the GCD of a and n is 1, so they're co-prime. Then, if we raise a to the power phi of n, we get something that is 1 modulo n. This result follows directly from the previous theorem if we look at the element a bar in the group Z mod nz star. Recall that the number of elements of G, the order of G, is equal to phi of n. If we specialize even further and take n to be a prime p, then we obtain Fermat's-Lidl theorem. Let p be a prime and a be an integer, then a raised to the power p is equivalent to a modulo p. If a is a multiple of p, then this is obvious. If a is not a multiple of p, then we can use Euler's theorem to show that a to the power p minus 1 is equivalent to 1 modulo p. Multiplying on both sides by a, we get a to the power p is equivalent to a mod p. Here are some quick questions. See if you can find the answers before moving to the next slide. The prime factorization of 2020 is 4 times 5 times 101. From this we deduce that phi of 2020 is 2 times 4 times 100 is 800. It now follows from Euler's theorem that a to the 800 is congruent to 1 modulo 2020. Again, using Euler's theorem, we see that a squared is 1 mod 4, a to the power 4 is 1 mod 5, and a to the power 100 is 1 modulo 101. This implies that a to the power 100 is 1 modulo 4, 5, and 101. In other words, a to the power 100 minus 1 is divisible by 4, 5, and 101, and therefore divisible by 2020. This implies that a to the power 100 is congruent to 1 modulo 2020. Let H be a subgroup of the group G. Let A be an element of G. Now multiply all the elements from H from the left by A. The resulting set of elements is called a left coset of H. If we multiply all the elements from H by A from the right, we call the resulting set of elements a right coset of H. Let's look at an example. For the group G, we take the symmetric group on 3 elements. The subgroup H is the group generated by the transposition 1, 2. For any element A in S3, we obtain a left coset of H. These are listed here. We notice a number of interesting properties of these cosets. The first property is that the subgroup H itself is a coset of H. The second thing we notice is that there are actually only 3 cosets. Every coset just occurs twice in the list. The third property is that all left cosets have the same number of elements. Finally, we notice that any 2 distinct cosets are disjoint. They don't have any elements in common. Now let's look at the right cosets. Here similar properties hold. The subgroup H is itself a right coset. There are exactly 3 right cosets. Every right coset has 2 elements, and distinct right cosets are disjoint. Note, however, that the right cosets are not equal to the left cosets. For example, the set consisting of the transposition 1, 3 and the 3 cycle 1, 2, 3 is a left coset but not a right coset. Let's consider a second example. As the group G, we take the integers with addition. As subgroup, we take the subgroup H consisting of all multiples of n. To construct a left coset of H, we take an integer a and then add it from the left to all the elements in H. So what we get is nothing but a residue class modulo n. Since the group operation is written additively, we write a plus H instead of a times H for the left coset of H. Since the group G is abelian, the left cosets are exactly the same as the right cosets. As an illustration, we can take n equals 5. Then the subgroup H consists of all multiples of 5. The cosets of H are exactly the residue classes 0, 1, 2, 3, and 4 modulo 5. In the examples, we notice some interesting properties of the left cosets of H. We will now set out to prove some of these properties in general. In the next theorem, we'll prove that the left cosets of H partition G. In other words, every element of G occurs in exactly one left coset of H. Okay, let's look at the proof. First, we want to prove that any element A in G is in some left coset of H. This is easy. The element A is in the coset A times H. That's because A is equal to A times the identity element, and the identity element is in H. We also want to show that every element is in at most one left coset of H. In other words, we want to show that the different cosets are disjoint. So suppose that we have two cosets, AH and BH, that are not disjoint. We have to prove that they are in fact the same left coset. Since the two left cosets are not disjoint, there must be an element that is in both. In other words, there must be elements H1 and H2, such that A times H1 is B times H2. Rearranging gives us that A is equal to B times H2 times H1 inverse. Multiplying on both sides by an arbitrary element H from the subgroup H, we see that any element A times H can be written as B times some other element from the group H. In other words, the left coset AH is contained in the left coset BH. By exactly the same argumentation, we also obtain that BH is a subset of AH. So we conclude that AH and BH are actually the same left coset. Suppose we have two left cosets of H, AH and BH. We know that these two cosets are either disjoint or the same. How can we tell if the coset BH is in fact the same as AH? The following theorem says that this is the case if and only if B belongs to the left coset AH, if and only if A inverse B belongs to H. To prove the equivalence of three statements A, B, and C, we only need to prove that A implies B, B implies C, and C implies A. This is what we will do. First, suppose that the two cosets AH and BH are the same. Since B is in BH and BH is equal to AH, this implies that B is in AH. For the second implication, assume that B is in the coset AH. This means that B is equal to A times little h for some little h in the subgroup H. But this means that A inverse B is equal to little h, which is an element of the subgroup H. So A inverse B is in H. For the final implication, assume that A inverse B is in the subgroup H. This means that there is an element little h in H, such that A inverse B is equal to H, or rewriting that B times E is equal to A times H. So that means that we found an element that's both in the coset BH and in the coset AH. But we know that if two cosets intersect, then they must actually be equal. In other words, the cosets AH and BH must be the same. Another property that we noticed in our example was that all left cosets had the same size. That this holds in general is the statement of the next theorem. The cardinality of every left coset is equal to the cardinality of the subgroup H. The proof follows directly from the fact that left multiplication by an element A gives a bijection from H to the coset AH. Consider any left coset AH of H. As we've seen in the previous theorem, if we pick any element B in this left coset, then BH is the same as AH. We call such an element B a representative of the coset AH. Now let's consider all left cosets. If we pick one element from each left coset, then together these form a system of representatives for the left cosets. Here are some quick questions. See if you can find the answers before moving to the next slide. Among the left cosets of H, only one is a subgroup, namely H itself. Indeed, the other cosets are disjoint from H, so they don't even contain the identity element. Here are the four left cosets of the set -1, 1. To get a system of representatives, we have to pick one element from each of the four sets. Here is an example. Let H be a subgroup of G. We use the following notation to denote the set of all left cosets of H in G. We have a similar notation for the right cosets of H. Most of the time we will focus on left cosets as we did in the previous theorems. For right cosets, analogous results hold. We define the index of H in G to be the number of left cosets of H. This is of course the same as the number of elements in a system of representatives. Let's consider a number of examples. In the first example, the index of the alternating group in the symmetric group is 2. One coset is AN, the set of even permutations, and the other coset is the set of odd permutations. In the second example, we consider the integers with addition and as a subgroup the multiples of n. As we've seen, the cosets are just the residue classes modulo n, so there are exactly n left cosets. In the last example, let's consider the integers as a subgroup of the rational numbers. A set of representatives of the cosets of the integers consists of all rational numbers that are strictly positive and small or equal to 1. So in this case, the index is countably infinite. We now come to an important theorem of Lagrange. Let H be a subgroup of G. Then the order of G is equal to the order of H times the index of H in G. If G is finite, this means that the order of H is a divisor of the order of G. The proof follows directly from the fact that all left cosets of H have the same cardinality. The theorem of Lagrange has the following corollary. Let G be a finite group and let X be an element of G. Then the order of X is a divisor of the order of G. This generalizes our earlier theorem where we saw this statement for the case that G was an abelian group. The proof follows from the fact that the order of X is equal to the order of the subgroup generated by X. We finish this lecture by an application of the theorem of Lagrange. We will classify all groups of order at most 5 up to isomorphism. Let's start with the groups of order 5. Suppose that G is a group of order 5. And let's take an element A in this group that is not the identity element. By Lagrange, the order of the element A must be a divisor of the order of the group, so it must be a divisor of 5. Since the order of A cannot be 1, it must be 5. This implies that G must consist of all powers of A, E, A squared, A to the power 3 and A to the power 4. In other words, G is isomorphic to the cyclic group of order 5. So up to isomorphism, there's only one group of order 5, and that is the cyclic group of order 5. Next, consider the groups of order 3. Again, we pick an element A that is not the identity element. Then by Lagrange, the order of this element must be a divisor of 3, but not equal to 1. So the order of this element is 3. And we see that G consists of the powers of A to the power 0, A to the power 1, and A squared. In other words, G is isomorphic to the cyclic group of order 3. So there's only one group of order 3 up to isomorphism, and that is the cyclic group of order 3. For groups of order 2, the same kind of argumentation holds. We see that up to isomorphism, there's only one group of order 2, and that is the cyclic group of order 2. Finally, we come to the groups of order 4. So let G be a group of order 4. If G has an element of order 4, then again G is isomorphic to the cyclic group of order 4. For the second case, suppose that no element of G has order 4. Let X be any element that's not the identity element. The order of X must be a divisor of 4, but it cannot be 1 and it cannot be 4. So the order of X must be 2. So this means that G consists of 4 elements, the identity element, and 3 elements X, Y, and Z that each have order 2. It's easy to see that X times Y cannot be the identity element, it cannot be X, and it cannot be Y, so it has to be Z. Continuing in this way, we see that G is isomorphic to the Klein 4 group. So we conclude that up to isomorphism, there are 2 groups of order 4. There's the cyclic group of order 4 and the Klein 4 group. Finally, there's exactly one group of order 1. This concludes the video lecture. Perhaps you can find all the groups of order 7 yourself, or, a little bit more challenging, all the groups of order 6.